Hello and welcome to the 2015 EMC Live Test Bootcamp. This presentation is how a new scanning technique can pinpoint emissions from inside an IC or microchip in minutes. My name is Graham Kilshaw. I'm the Chief Media Officer of Interference Technology, and we are the creators of EMC Live. The Test Bootcamp is a free one-day event focused on the test and compliance side of EMI engineering. Today's presentations will also cover enhanced EMI characterization, the limitations of rod antennas, understanding chambers, and how to choose the right test antenna. So join us for all of these topics today. Just register at the EMC Live Test Bootcamp website. This webinar is presented by Rutger Patton. Rutger's joining us from Canada, and he's the Director of Product Management at EMSCAN. And he's responsible for the evolution of EMSCAN's real-time near-field measurement solutions. Rutger holds both a BSc and an MSc in electrical engineering from the University of Saskatchewan, and during his time at university he was recognized with numerous IEEE awards and a distinguished research scholarship. EMSCAN is a world-leading developer of fast magnetic, very near-field measurement tools. They provide real-time lab bench systems that are both efficient and cost-effective and eliminate the need for an anechoic chamber. They also offer accelerated time to market to liberate PCB engineers, antenna designers, and wireless engineers. So attendees, before we begin, a few notes for the many hundred of you who have registered for this event from around the globe. First, since you've already registered, you will automatically be sent an email next week when a copy of Rutger's recording and presentation slides are available to download. So no need to email us. Second, the presentation is interactive. So please do send in your questions during the course of Rutger's presentation, and we'll answer as many of them as possible at the end. To send in a question, just use the chat button on the right side of your screen. And if you wish to minimize or maximize your screen at any time during the presentation, simply click the red arrow button in the top right area. Rutger's presentation lasts about 35 minutes, and it'll be followed by a 10-minute question and answer session. And now, Rutger Patton of EMSCAN will begin the presentation. Over to you, Rutger.
Okay, thank you. So we'll get started. First of all, just give a bit of background on EMSCAN and what we do. And then we'll get right into the presentation, starting with the description of what we call very near field. We'll talk about a test solution for this type of testing, and then we'll show the results when we get into very high resolution testing. The sample results will be focused on using these to help fix EMC issues, and in particular looking inside the IC to identify the different frequencies and locations of emissions inside the IC. We'll also talk about the possibility of using these near-field emissions to predict far-field results. So EMSCAN is a company that focuses on what we call fast, very near-field testing. The products are based on arrays of sensors, which allow us to very quickly sample the magnetic field distribution and either display this in a visual sense to help identify sources of location, or to take this information and transform it to the far field and even predict the parameters for antenna performance like gain, efficiency, and radiated power. Our tools are what we call pre-compliance, so they're not meant to replace the EMC testing at the end of the day or the chamber testing. So EMSCAN has really two different product families. The first one, EMXpert, is related to the EMC testing, and that's what we'll be talking about today. The other one is RFXpert, and although this uses very similar technology, the application is really focused on antenna testing or wireless device testing. So now on to what we call very near field. I always like to start with this in my presentations because it gives an idea of what we're testing and how we're testing it compared to other techniques. In fact, when we call the region very near field, what we're referring to is the reactive region. So with a typical device, and this can be an antenna or a circuit board, we have different regions where we have propagating fields in the far field, where there's also propagating fields, but they haven't established a consistent pattern, what we call the radiating near field. And then there's a region very close to the device where we have radiating fields as well as stored energy. It's in this reactive region where we have this stored energy where the EMSCAN tools do all of their testing. Typically, in this region, we have to be concerned with interference between the device and the product under test, especially when we start looking at antenna testing. For the EMC testing, we're able to test in this region typically because PCBs aren't as sensitive to the disturbances. But it is something that we have to keep in mind as we're doing our testing. So of course, what we're eventually most interested in for EMC testing or antenna testing is what we are referring to as the far field or chamber measurements. These are very specific tests, especially when it comes to EMC. This is the type of test that we have to go through if we want to qualify our device. But really, this type of testing only tells us if it passes or fails. It doesn't add a lot of value in understanding what's happening and what's the root cause of any sort of emissions. That's where we come to maybe the traditional very near field testing. Many people, if they're doing board level debugging, are probably familiar with near field probes, sniffer probes. This is a very useful tool in identifying the source of locations of the emissions, but the problem is that this is very slow, and you're also likely to miss potential sources of emission. Because you're sniffing around one point by one point, you don't have a picture of the entire board. Now, there is solutions that will take that single probe and move it methodically around the board under test using some sort of robotic positioner. These are, of course, better at identifying emissions over the entire board, but they become very slow. So this is where we come to a new very near field implementation. As I mentioned, the EMSCAN tools are based on an array of probes. So shown here is a picture of a segment of our array, and you can actually see the small probe elements. Each one of those crosses represents a magnetic probe, which is essentially a small loop embedded directly into a large circuit board. So by switching between these different probe elements, we can sample the field distribution of the magnetic field at each one of these probe locations. Because there's no mechanical motion, the system is much faster and also more repeatable. One of the drawbacks of this approach, though, is that spatial distribution. You can see that the probes are basically packed in as densely as possible in this case. So even though they're spaced at only 7.5 millimeters, when you want to get to very fine details, this approach might not work. This is an overall view of what a system looks like. So you can see there's a sensor array. Really, the array of probes is the key feature of the sensor array. The output of this array is actually fed to a spectrum analyzer. So in fact, it's the spectrum analyzer that's doing the measurement. This is a useful tool for identifying very low-level signals and for identifying specific frequencies of all these signals. The controller will synchronize the triggering of the spectrum analyzer and the switching of the probes so that when the data is transferred back to the software, we can reconstruct the locations where each one of those measurements was taken. And this allows the software to essentially draw a picture not just of the different frequencies, but also spatially where they came from. So shown here is maybe a sample result. This is what we call the spectral scan. So testing under several of the probes, or maybe many of the probes underneath the circuit board, we can identify the frequencies that are being radiated from this device. Really, this step is just to identify the frequencies, since this is not going to add much more value than any of the other types of testing. You'll see the same frequencies in this test as you would see in the chamber, and you'd see the same frequencies here as you would with the sniffer probe. What that spectral scan does do is sets us up for the spatial scan. This is the one where we now have a lot of information about where those different frequencies are coming from on the board itself. So shown here is an example of what this might look like. At one of those particular harmonics, we can see the distribution of energy or currents around the board. Overlaid on top of this measurement, in this case, is a design file or Gerber file from this circuit board. So in this view, it becomes very easy to immediately correlate different features of the board, components, traces, with the actual source of emission. And when seeing this, it gives the designer or the debugger a good intuitive sense of where those emissions might be coming from. And more than that, can tell them what the actual mechanisms that are causing it to radiate are. So in this case, we can see that there's possibly a large loop of current around the top edge of the board. This loop would be an effective radiator and should be dealt with at a board level before this product ever goes for EMC testing. So we talked about the benefit of this near-field technique is that it's very fast and repeatable, but it's lacking the ability to go to very high resolution. So this is where this new technique comes into play. We essentially use the same array of probes that we've already seen, but we will actually move these probes so that we can get effectively higher resolution. Shown schematically here is what several elements of the probes might look like. At column A1, there's a single probe element embedded in the center of this large box. These probes are actually smaller than the ones we saw originally with the cross, but they're still not packed in any tighter. The spacing is still 7.5 millimeters. By combining together that array of probes with some amount of small mechanical motion, we're actually able to synthesize a much higher resolution array. So this concept is actually illustrated here. At level 1, which is basically the standard resolution of the array, we have a measurement probe every 7.5 millimeters. But we can actually move the entire array, all 1,200 probes at the same time. And you can see what would happen then for a level 2 scan, which is half of the spatial resolution. The probe array would first move into the top left corner of a sub-grid, do the measurement of all 4 points, or all 1,200 points as it may be, then move to the second subgrid, the third and the fourth. So the same array of probes is moving to 4 different locations. So the amount of mechanical motion has been minimized here, and we can support up to over 4,000 measurement points in this case. The software knows exactly where these measurements came from, so it can reconstruct them in that final view of the level 2 scan with essentially twice the spatial resolution as the original measurement array. This process is repeated for increasingly higher and higher levels by essentially halving the spatial resolution each time. So by the time we get to a level 7 scan, the spatial resolution between measurement points is only 0.1 millimeters. So this is an example of what this increasing resolution might look like. This is a zoomed-in area of a circuit board, and we can see approximately on the left in the level 1 scan where the energy is coming from. We can resolve those emissions down to about the 7.5 millimeters, which is the spatial resolution. But it doesn't give a lot of detail in terms of the trace or component that might be coming from. As we increase the spatial resolution, going to a level 3 scan, you can see the grid has in fact shrunk, and it would be a quarter of the spatial resolution in this case. And even by level 3, we can start to make out a lot more details and can certainly follow this particular trace on the circuit board, seeing the currents flowing along that trace, which are generating the magnetic fields that we're measuring. So now we'll show some sample results of different boards that we've tested. The first one is a large circuit board. So this is where that image had just come from. And we can see in this view what we call the spectral spatial. So this is actually combining together the best of both worlds. We can see the spectral emissions. There's clearly some strong harmonic signals, and also some broadband emissions. We can see the entire distribution of the board, a complex mishmash of all of these different signals, and it gives us an idea of where the major problems might be in the circuit board. The software allows you to jump around by frequency or by location to actually follow these signals around the board. You can load different layers of the PCB, so you can look, if you have a multi-layer board, signals might be coupling from one layer to the next. So as you follow that trace, you can see in this case, the energy might couple to a different layer. You load up that other layer and identify the feature where that is radiating from on that board. In this case, we've identified energy that is coupled onto a power plane. So as that strong red signal in the center went underneath the power plane, it likely coupled onto there and could cause issues now propagating around the board on that power plane. We can also see some energy that's coupled onto a control line. So this might cause issues in terms of performance, or again, coupling that noise around the board, maybe even exciting another radiating structure and causing emission problems. To highlight these ideas as well, what we'll do is actually switch over to our software where we have these results. So we can now show how this software can work in practice. And it's a very useful product because, as I mentioned, we can very easily switch around by location and by frequency. So this is showing the entire spatial distribution of the board and the entire spectral distribution of the board. Going into the spectral view, I can zoom in on one of these peaks and select it. By putting a small X on the board, I can actually identify not just the entire spatial distribution of all combined frequencies, but I can isolate just that single frequency. Changing the scale allows me to focus in on the specific features that I'm interested in. So as I go around to the other harmonics in this board, I can see if they're all related. As we go up in frequency, we might notice that the resolution or the coupling features on the board are changing. So even by the time we get to 240 megahertz, we can start to resolve the specific trace that was coupling this clock signal onto a different control line. At 280 megahertz, it's very clear that there's one signal going on this clock line coupling onto an adjacent signal and possibly causing problems with emissions or performance of other components. Now we also have the ability to go in to the spatial view. So there was some energy coupling down onto this control line. If we select this area of the board, we can look at the spectral distribution from just this location. Compared to the entire board, we see that it's actually missing a lot of those strong harmonics. So in fact, what's happening in this area of the board is it's not coupling that same signal that's present on those other two traces. There's some other feature, some other noise signal that's being radiated here. By coming into the spectral view again and selecting some of these wideband signals, you can actually see that's what's radiating from this control line down at the bottom. As I select multiple signals and combine together those into a single view, I can get a good picture of what that spatial distribution on that control line is coming from. So this very clearly indicates that I have two different problems. One is a harmonic of probably 40 megahertz. The other one is a broadband signal, probably coming from some sort of switching mechanism. But the ability to very quickly switch between different frequencies in my scan and isolate different frequencies in different locations is another very powerful feature of having this near-field testing with a powerful software like this. This is an example looking at that control line where we can actually follow it down the trace, see where it transitions by this via onto another control line, comes down, turns the corner on this control line, and then actually runs behind a ground plane. So that's why it's only visible in a small portion of the board, because in the rest of the board, it's actually shielded with the ground plane. So the next step is to go in even higher detail. That gave us an entire board level view. But now we can actually peer inside an IC. So in this case, what we've done is actually taken a photograph of an IC. The die has been exposed, so we can actually see it inside the chip itself. And the results have been overlaid in our software directly on top of a photograph rather than on top of a Gerber file. We can see here some different results. And looking inside the board, we can actually see where they're radiating from. 100 megahertz coming from just the die region itself. 120 and 130 megahertz look to be coupling out down some of the pins on the IC. At 120 megahertz, we can actually see energy coming from a different portion of the board that's spilling over into the same location as the IC. So it's possible that this energy is coupling into the IC rather than being generated in here. This type of information is obviously very useful at identifying what frequencies are present, but it still requires some understanding of the design itself to give the designer the best chance at resolving issues. So understanding whether or not 100 megahertz is used inside the IC, is it generated there, is it a multiple of an external clock signal, combining that together with my measurements with these spatial results gives me the best ability to understand this product or this design and come up with solutions for possible emissions problems. We can actually see the timing here. So each one of these different frequencies is isolated from the spectral spatial, but the entire spectral spatial scan took only 2 minutes. So once we have that data, sampling between these different frequencies or any others that are present is instantaneous, as we saw in the previous demo with the live software. This is another example. Very simple to take off the case of this. In this case, it was a solid-state drive. Take off the metallic case, which would act as a good shield, and lay the board on the scanner. Very easy for setup. The idea is that we want to be as close as possible to the measurement probes with the product that we're testing. In this case, we can see in the spectral view a lot of different harmonic frequencies. And if we look at the measurement results, again, we get very high resolution views of the entire board, and we can actually peer inside the different chips on this board. We can see the view in the center picture of the actual memory chips, each one being an identical chip, and you can see that, in fact, the distribution of noise inside each chip is very, very similar. What is happening is that we are sending signals possibly from the controller, which is shown in the right, over to these different chip modules. So because of the high speed of this testing, not only do we get this beautiful high-resolution scan, but we can test different performance characteristics of this product. So as it's doing different functions, booting up, accessing memory, writing to memory, reading from memory, because of the high measurement speed, we can actually get the distributions in these different functions. So it allows us to more thoroughly characterize the performance of the device and pick out issues at specific operating conditions that we might otherwise not see. Now the question is this comparable to other techniques? So the obvious one is the single probe method. So what we've shown here is one done with robotic positioner and with a rigorously organized handheld probe. So the handheld probe one was actually done in the software for the EMXpert as well. And the software will actually prompt you to position the probe in a specific location. So this takes out some of the guesswork in doing the single probe sniffing. And once that data is collected, it also allows you to get the visual representation that's shown here. But what we can see is clearly the probe array method and the single probe methods give very similar results when looking inside the IC. So what we can do now is actually combine together these two scans. We can look at a very large board level scan, identify gross effects that might be radiating from the device, and if these lead us back to an IC, we also have the capability of peering inside that IC and identifying exactly which features in there are creating those signals. So this is an example of testing at a board level, we can see that there's some very strong signals coming from this board, centered in the middle of the board itself with the strongest levels, and that energy couples around on different traces. From the spectral view on the left, we can see that there is a lot of different types of energy happening here. There's different harmonics. There's also broadband noise. All of that's combined together to create quite a noisy product. Having the ability to isolate by location, we can take that same data and select the chip out of this area. With the basic coarse resolution scan, you can see that there's only 6 measurement points or 6 crosses underneath that one chip. But it's enough for us to identify what the spectral emissions are coming out of this product. We can see that a lot of the strong harmonics are not present at all in this chip, but there are still a significant portion of them coming from here. Taking that same information and now looking at the spatial distribution of the energy, we can see a very interesting effect happening inside this single chip. The entire distribution for a high resolution scan from 50 to 500 megahertz shows the basic area that's radiating, but very distinct areas at different frequencies. So clearly there is something going on inside the chip where these different frequencies are handled differently. Whether this is an intentional effect, different frequencies feeding different areas of the chip, or it's unintentional, where we're getting harmonics that are coupling randomly across different features inside the chip. Without knowledge of the chip itself, that would be hard to discern. But if we did have design knowledge of the chip, this would immediately tell us what effects are happening. For this one, I'll also switch over to the software, just so we can see this operation happening. So this is the chip level testing. We can see the many different frequencies here. And if we come into a region of the spectral noise, choose a very strong harmonic, and isolate that, we can see the different features and how easy it is to now select the different areas. These ones are very strong single points, possibly generated by a random event. Now this random event wasn't captured in this case, but with this high-speed testing, we could run this test continuously and actually build up a picture of this random event. So even though only one scan was captured here, by testing many times, we will eventually capture the distribution at different regions. And even with that very, very infrequent event, we could capture a detailed high-resolution scan like this. So this is showing by spectral view, and again, we have that same capability to test by spatial region. So selecting one area of the board and looking at the spectral distribution, we can identify what frequencies are coming from different areas. As we select different regions of the board, we can see how the spectral plot changes. So again, once this test is run, taking just a few minutes to test, we now have the ability to, in post-processing, evaluate all these different frequencies and how they actually occur inside the chip. The last portion of the presentation will deal with using this information for EMC far-field prediction. We've seen how we can do it at a near-field level to give an understanding of where the emissions are coming from. But we've said that the designer typically would have to have, or the tester would have to have, knowledge about the design intent, combining together their experience and understanding of EMC problems or best practices. They can have an effective solution. But at the end of the day, they don't know from the near-field testing whether or not the product is going to pass or not. So what we call far-field prediction takes that final step. It's not a compliance test, but it will estimate what you would see from a given board if it were to be done in a compliance test setup. So here we can actually see comparison between an actual measured result in red and the far-field prediction based on near-field testing in blue. There's obviously some discrepancies because this technique can miss some information, but in a general sense, it gives a very good estimation of the approximate level. certainly telling you if you have a concern or not when it will come to the compliance testing. So the way this works is, in this case, you can see a case study with a very simplified design so that we can make very accurate comparisons. This is just a simple PCB with traces, a resonance structure or a passive resonance structure, and a conductive trace, measuring the near field, separating the two different polarizations and including phase information in this case. This data is then imported into a software. So there's two different types of software that we work with right now. One is a full wave simulator, like some of the major vendors already out there. And they can import this data, create an equivalent source surface, and then model the overall effect of that board. This one is very useful because now you can start to put in surrounding components. You could put in ground plane, covers, cases, other structures around this PCB that might affect its radiation profile. The simulation then will take those into account and give an overall view of what the emission levels are in the far field. The second technique, which is actually the one that generated the far field results we saw, doesn't need the phase information. It actually uses a model-based approach and can approximate the far field emissions, but only at the PCB level. So in fact, that is one of the limitations of both of these techniques right now. They're primarily focused on the PCB itself. So in some cases, this is the major radiator, especially if we're looking at small components like ICs. But in other cases, you have to be concerned about the cabling, power cables, data lines, which can be a very good radiator and a major source of emissions in many cases. So this is the current limitation of this far field technique. But if you do have a case where the emissions are isolated to a single board, we can see that there is very, very good approximation between measured level and the equivalent source model, which is what we showed where we put into the software. This is still something that's under development both with ourselves and our partners, but it's certainly the way that we hope to move forward with the far field predictions in the future. Okay, so what we've seen is that the array-based technique is very fast at identifying sources of emissions. It allows us, because of this real-time aspect, to test many different board designs, to identify potential problems in the EMC perspective before we go to testing. And if we have different functional versions of the board, if we have intermittent or profiles that change with different features, we can actually capture that again because of the high-speed testing. And when combining this together with the very small spatial, mechanical motion, we can actually create a very high-resolution test system that doesn't lose these other advantages of being high-speed. Now, we do have some of the limitations, and one of them is that this is mainly for PCB diagnostics, not for product compliance. So it can help us, especially if we have understanding of the board design and intent. There's possibility for this to give some estimation of far field, as we saw, but it's not quite there to actually predict the compliance result from a system quite yet. We did mention, especially when it came to high-resolution testing, that we do have to be very close to the board under test. So this means that some shapes are not appropriate for testing. We need that device to be close to the scanner array to get the high resolution. If it's separated from the array of sensors, we may be able to pick up the information, but we won't be able to spatially resolve where we measured that information from. So that ends the presentation. And what we saw in those test results was basically demos from customer boards. And this is what's most interesting to us. So if you ever have an opportunity where you want to test one of your boards on an EMXert system, contact us and we can come out and essentially do that in a demo purpose for no cost. So thank you very much.
Thank you, Ruska. It's a very important presentation. As devices and systems get smaller, the ability to measure and see the emissions on the board and at the chip level at high resolution, I think, becomes ever increasingly important. So this is really good stuff. Attendees, this is your last opportunity to send in your questions. Please enter them now in the chat field on the right side of your screen. We'll take the first question in a moment or two. And while we're waiting for those last few questions to come in, I'd just like to let everyone attending know that more information on this subject and scanning for emissions at near field and very near field levels can all be found on the EMSCAN website, emscan.com. So Ruska, here's our first question. This attendee is asking, I have an RF noise issue in a GPS design. The PCB size of the GPS board is 36 millimeters by 19 millimeters. Do you think your system will help to detect the source of the noise?
Yeah, so this is actually another application for the EMXpert system. It's not the typical EMC problem. It's what we call desense or self-interference. We have tested products like this exactly for that purpose, where the product is generating its own noise that's affecting a very high-performance receiver on board. So we have, in fact, had success at identifying and tracking down noise sources at very low levels. In fact, I think the sensitivity for the EMXpert system is about minus 130 dBm in some cases. So that can certainly give you a good opportunity at tracking down the source of the emissions. It's absolutely worth a try. Okay.
The question again, Ruska, was, is it possible to integrate your scanner in a bench test?
Yes, so one of the things that we provide is what we call a programming interface for the software. So if you have an existing test solution or test setup, you can take the system and integrate that directly. You can ask for measurement results from the software. So, for example, if you're doing comparative testing, if you want to evaluate the quality of your production or do screening of quality, you can do that in an automated sense with the equipment.
Okay, next question. Can we apply this technique to FEM, front-end module and power amplifier?
Sure. So what we're doing is simply measuring the magnetic field next to the device for testing. What that's going to identify is where those currents are on the board. The actual device itself, we don't care about the application, but for power modules and front ends, if there is significant emissions in the frequency range we detect, we will be able to identify different components and traces that are essentially conducting those currents on the board level. And I don't know if it was mentioned here, but the frequency range for the product is between 150 kilohertz and 8 gigahertz. So it covers a lot of any sort of RF concerns as well as any low frequency switching components that you might have.
All right, we've got a two-part question now. What's the maximum power tolerable by the scanner, and what's the maximum detectable frequency?
Sure, so maximum frequency I just mentioned was 8 gigahertz. Maximum power, in terms of a radiated power from the device, is about plus 40 dBm, so that would be about 10 watts. In terms of voltage, the breakdown voltage of the system is above 9 kilohertz. So you can put some pretty high power components on there, and they can even be very strong radiators, and the system will be able to manage that.
Okay, 4 more questions left. Let's see. Is the movement inside the EMSCAN unit?
Yeah, so the high-resolution scanner that we've developed, essentially the product under test will sit on the surface and not move, and underneath the product, this entire scanning array will shift around slightly. It only moves by a few millimeters, but it's enough that you can notice it moving while you're doing the testing.
Okay. And what's the typical total scan time, Ruska, for a level 7 scan?
Sure, a lot of that depends on the amount of probes that you're testing and the frequency span that you're testing. For a level 7 scan with an area of about 1 inch by 1 inch, so much bigger than a typical IC, the scan time might be as high as 18 minutes, depending on the spectral resolution and spectral span that you're looking at.
Okay. Here's an interesting question from Ken Wyatt in Colorado. How well does this work for multi-layer boards? They may have embedded clocks, high speed, or power supply traces within return planes.
Right, yes, good question. And we kind of saw that effect in one of the measurement results that we saw. Really, if it's on an internal layer that's well shielded with, say, ground plane, there is really no emission outside the board to detect. So in that case, we don't see any signals. Where this becomes useful is if you have emissions and an internal layer, and those are leaking out of the board. So whether that's at the edge of the board, or if there is maybe a slot or a hole in the ground plane and you have energy radiating out of that slot, anytime that happens, which if we're looking at an EMC problem is really only when you're interested in it, the fact that we measure over the entire board is very beneficial in this case, because you'll actually pick that energy anywhere where it leaks out of those internal layers where it's not well contained. We'll pick that up and actually identify that location so that it can be rectified in the design.
Okay, and here's our last question. The attendee is asking, many of us, I guess a group of them, recently participated in a software simulation presentation. Can you describe where and when the EMSCAN product would be used?
Sure. So when I talked about what I call sometimes that co-simulation or the source reconstruction, essentially what we're doing there is we're taking out the most difficult challenge for the software simulations right now. They can measure the large level effects. They can even measure very small features in some cases, but they can't really combine together large systems and small features. So if you're looking at something like a PCB with many different ICs on it, small traces going between layers with other passive components, this is very hard for the software to accurately simulate. So what we would do in that case is actually measure the near fields coming out of this circuit board. It means it has to be physically created first, but by measuring the fields, we basically bypass all of the difficulties in simulating those very small features. Now that we've measured from the small features, those are imported into software and become a source on their own. And now you can start to play around with, in the software, integrating that PCB into a larger system. So you can take what used to be your PCB and now is just measured sources, plug a larger system, combine together chassis and slots in the chassis and other components, and see how at a system level this device radiates. So that's kind of how the two measurement and simulation packages complement each other.
Thanks, Ruska. Great set of questions there, I think, and great answers too. We received a lot of questions, but unfortunately we're out of time now. Attendees, if any of your questions were not answered, don't worry. We will capture all of those questions, send them over to Ruska and his team, and we'll post all of the questions and answers on the Test Bootcamp website within the next week or two. Just sign up for the Interference Technology newsletter, and that's how you'll be notified. I'd like to thank Ruska and all of his colleagues at EMSCAN for their time and expertise today. This was a really informative, very useful presentation, I think. Thank you to you, all of our attendees around the globe. I'm Graham Kilshaw from Interference Technology. Join us in just 15 minutes from now if you'd like to get a good understanding of EMC chambers. Promises to be very interesting. You'll have time to register for this. You've still got 15 minutes if you wish to join us. We'll see you again very soon. Thank you.